All right, so I'm Nicole. I'm a Forrest Fellow at Ipper Curtin, and today I'll be talking about kind of a deep dive into an aspect of radio interferometry that might scare you. Something that Dee said the first day kind of resonated with me in that, like, the activation energy to get into radio interferometry is quite large if you're not used to it. So hopefully this might either scare you away or you might learn something from it. I don't know. Briefly, what is interferometry? This is going to come up. Interferometry measures visibilities. Visibilities are a function of the beam response of the instrument, the sky intensity, so what you're looking at, and a geometric phase term or sampled mode. And this sampled mode depends on the distance between your antennas or your baseline and the wavelength of light that you're looking at. And there is this idea that that you can reconstruct the image of the sky through the mutual coherence function if the source you're looking at that you want to see is infinite distance away. Essentially, what this means is that this is a Fourier transform, a double Fourier transform of the sky. The problem that we're seeing is that this A term, this beam sensitivity term, for a wide field instrument is not simple. So you measure these things. These are visibilities. You get a function as you get a point as a function of frequency, and you get a visibility per pair of antennas. So you end up getting like 4 million visibilities every 2 minutes. It's a big data problem, especially since if you want to recreate images, you have to take FFTs of 4 million visibilities over 384 frequency channels, let's say. So there's a lot to do, but you can recreate the image of the sky. And so this is what the MWA sees for a 2-minute snapshot. I've removed all of the sources that I know about. So this is a residual image, which is important for epoch of reionization science. And I'm plotting the image down to the 1% beam sensitivity level on the white lines here, which is a bit further down than what you would normally see with an image. And you should be able to tell in this hash of residual stuff is that as you get closer to that white line, you get very bad sensitivity. It becomes noisier as you get towards the beam nulls. But at the center, at this primary load, you have very good sensitivity. It's far less noisy. And so a question that Aman and I asked back in 2022 is, rather than use this really complicated AS term, this beam sensitivity term that we get from FECO simulations of electromagnetic, basically from the ground up the dipole all the way through the system. Instead of using that term, which is again complicated, if you can decompose that term into a series of Gaussians, which are analytic, and their Fourier transform, what does your image look like instead? And it looks much cleaner. Again, this is the same observation, a residual again, and you can tell, especially as you get towards those white lines, that the edge of the beam, the noise has greatly reduced. And so what I'm getting at here is it's not that the visibilities have necessarily changed, is that we've improved our analysis systematics, and that has contributed to a better image at these low beam sensitivities. Cool, so that's all well and good, neat. But what that means is that we can go further out into the image and see more than we could before. So here's that same image all the way out towards the horizon in right ascension. And you might be able to tell that there's a bit of an issue here, something that I forgot to remove. It's the galactic plane. And I forgot to remove it because it was setting, so I thought it didn't really matter. I thought, well, it's at 1% beam sensitivity. How bright could it really be? Well, the galactic plane is quite bright, and in fact, in this residual image, it's the brightest thing left over. Again, just to reiterate, this is going all the way out to the horizon. This is actually quite difficult to do for radio interferometric data if it's something that you've been working with for a while. It's almost impossible to do with a lot of the older software. And that's because that older software is built off of doing science in the primary lobe. They're quite bespoke for doing not horizon to horizon imaging. So really being able to see this galactic plane for the first time is really a result of having the infrastructure in order to do so, making code bases that can handle horizon to horizon imaging. So let's take a closer look at this galactic plane. This is a model of the galactic plane as it's setting. This is using the same basis as the NWA observations that I'm looking at. And the galactic plane model is coming from the Engineering Development Array, or EDA2. And this is thesis work from Mike Creel, which culminated in a paper in 2022. And you can tell that this galactic plane is setting over the course of the night. And that's done on purpose in a way, because for EOR observations, you want a quiet, relatively cool part of the night. And so you don't want to look at the galactic plane. You want it to set. And trying to model this is actually quite difficult, because even though Mike provided me this beautiful spherical basis function that he had created for the galactic plane, I couldn't use it like that, because this AS term, this beam sensitivity term, has a large gradient as you get towards the edge, which means over a spherical basis function that you have, the AS term is changing drastically, which screws up the analytic portion of the Fourier transform, the whole point of using a spherical basis function. So we had to decompose it into a series of point source functions, or point sources. And to do that, you need a extremely powerful GPU simulator, because that's quite a lot of point sources. Luckily, Jack Line made such a powerful GPU simulator. It's called Woden, and he published it in 2022. So I was able to take that beautiful model that Mike made, put it through this beautiful simulator that Jack made, and this is what it looks like out of an interferometer. This should scare you. This is bad, right? This does not look like that. And the reason being is that your interferometer measures something in Fourier space. And if something is quickly cutting off in Fourier space, you're going to get aliasing. And this is natural to the measurement itself. This is unavoidable, essentially. And it's quite disturbing. So what does this disturbing thing look like from the MWA's point of view? Well, your MWA is a dipole. Well, it's a lot of dipoles, but at its core, it's a dipole, and you get two polarizations out of this dipole-dipole crosspair. You get a north-south dimension and an east-west dimension, which you can build your Stokes parameters from. And so here are the two polarizations, which each have a slightly different AS term, a slightly different beam sensitivity, as you can tell. They are related, but you can see that the aliasing of just the galactic plane, again, just the simulation put through this MWA Gaussian decomposition of the beam, you can see the aliasing is quite a big issue, and it actually aliases throughout the entirety of the image and in both polarizations. So that was all great. That was all simulation, right? So let's look at it in that 2-minute snapshot. If I remove the galactic plane model that I got from Mike and use Jack's simulator to do, you can see that it goes away lovely. And not only can you see the galactic plane being removed in 2 minutes of data, you can see the aliasing throughout the entirety of the image, if you squint hard enough, being removed in 2 minutes of data. This is actually quite a big effect, which is surprising given that the core of the issue is happening at a 1% beam sensitivity level. So you might ask, oh my God, what about my science? How will this affect my science? Luckily for the majority of people, you're probably fine as long as you use a range of LSTs to do your science. as long as you're not just using a subset of observations which are fully affected by this galactic plane setting. As long as you aren't looking at scales that the aliasing is present on, and as long as you are fine with an increased noise in your statistics, which for EOR people, that's not fine. So it's something that we worry about. So one other question you might ask just really quickly, all right, cool. So you see this horizon edge, this bleed coming from it. Why don't you just remove the horizon, right? Why don't you just do a single Gaussian for your beam sensitivity term instead of all the way out to the horizon? Well, it's not quite that simple, again, because the inherent measurement went all the way out to the horizon. So you can pretend like you didn't see the horizon, but it's still there in the measurement itself. And so if I just use a single Gaussian to model the instrument, it actually looks much worse. And that's because I'm folding in all of the information from the visibilities into a smaller space. So just to throw a power spectrum out there for the EOR people, we're doing better than before. So on the right here is from 2019, and here's on the left here, current day. So we are noise limited at this point in time, so we're continuing our analysis. I'd be remiss if I didn't mention that there's a lot of things going into this, these new limits that we'll put out, and it's really a group effort. And just to skip that, I'll go to my summary here. The galactic plane aliases in interferometric radio measurements when it sets over the horizon, even if it's at 1% beam sensitivity. And we need to account for this beam horizon interaction. And the EOR team is making strides towards a new limit. Thanks.